All right, I'll begin with a word of prayer once I get over here. Dearly Father, we thank you again for this class and for this opportunity we have to meet and study your creation. Just pray you guide our steps, help us to understand a little bit more about differential forms and many things they can describe, Lord. In the name I pray, Lord Jesus. Amen. So, I'm going to begin with a proof of what's known as the Poincaré Lemma. And, but before I do that, I really should give you a few definitions and tell you a little bit more about what's going on with all this stuff. So, definition. If omega is a, let's say, P form on a manifold, and d omega is equal to 0, then omega is closed. So a closed form is simply one whose exterior derivative is 0. On the other hand, if there exists, let's say, phi, a p minus 1 form on M, such that the exterior derivative of phi is equal to omega, all right, then omega is an exact form on M. All right? So this is closed forms. These are exact forms. I think it's helpful to come up with a name in this case. Let's say that phi is a potential form for omega. Now, of course, we could talk about these ideas locally, right? We could look at a subset of a manifold and just talk about a differential form being closed on that subset and being exact on that subset. So you could localize these ideas, talk about locally exact, all right? And that would be a good idea. Because oftentimes that's all you can get. You can only get local exactness. You can't get globally exact as it happens. So what do you think? Is there any kind of theorem you can see here? How about this? If omega is exact on M, then omega is closed. Right? Why is that? If we have d omega is equal to d of d potential, well, that's d squared, right? Which we've already proved is 0. Remember, the exterior derivative, when it hits twice, it gives you 0. So I have this as proposition 10.10.3. I say all exact forms are closed. However, there exist closed forms which are not exact. All right, so what's an example? So the converse of this is not generally true, okay? There exist closed forms which are not exact. Let's see here. So here's an example of that. Example 1. How about this? We can look at the form here, omega is equal to, let's say, minus y dx plus x dy divided by x squared plus y squared. Okay. And that would be on what? This is on M, which is, let's say, R2 without the origin. Right? The punctured plane. All right? So if you calculate d omega, you get, you know, partial y of minus y over x squared plus y squared dy wedge dx plus partial x of, well, x over x squared plus y squared dx wedge dy. But this is exactly, you know, minus x squared plus y squared plus 2y squared divided by x squared plus y squared. And there's a minus out here, plus parentheses, you know, x squared plus y squared minus 2x squared divided by x squared plus y squared. I forgot the square on the denominator over here, my bad. So doing quotient rule, and I switched the order of the differentials on the first one, right? So altogether then, what you got is you got x squared plus y squared times 2, and then minus 2 times x squared plus y squared. So the numerator works out to 0. So this is 0. Again, that's for, you know, x comma y not equal to 0, 0. Of course, at the origin, the calculation breaks down. So therefore, this is a closed form on the punctured plane, right? Consider this. If omega was equal to the differential of a potential function, right, then the integral of omega over the, you know, unit circle, right, would be equal to the integral of the differential over the unit circle, right, and that would be 0 because of the fundamental theorem of calculus, right? But here's the rub. However, the integral of omega over the circle is literally the integral from 0 to 2 pi of, well, you got yourself a minus sine t times minus sine t dt plus cos t dt divided by sine squared plus cosine squared, or rather cosine squared plus sine squared. So all I've done is parameterize the circle with x equals cosine t, y equals sine t, and literally plugged it into the differential, done the integral. Well, I haven't done the integral yet. The integral, though, is 2 pi. So obviously 0 is not equal to 2 pi. That's a contradiction. Therefore, no potential function exists for omega on the punctured plane.
Why is this 2 pi?
Sine squared plus cosine squared. So you get 1. That's 1. This all simplifies to dt. Yeah. So therefore, thus, omega is not exact on R2 with the origin removed, right? Yet omega is equal to the differential of the argument, right? That is what it is. I mean, it's, if you like, it's d theta. The thing is, the rub is that you can't define theta full circle without having the 2 pi degeneracy jump somewhere. Consequently, this form is closed on the punctured plane, but it's only locally exact. It is locally exact. Locally, you can write omega as the differential. All right, so that's one example that illustrates the converse doesn't work. Another example would be to think about the Coulomb field, this guy, you know, x, y, z divided by this, the square root of x squared plus y squared plus z squared squared. So in terms of my handy-dandy spherical frame formulas, it would be like rho hat over rho squared. It's the Coulomb field. It's the electric field of a isolated point charge at the origin, or you could think of it as the gravitational field of a point mass at the origin. It obeys an inverse square law, inverse reciprocal square law. So if I was to look at, for instance, the flux form of this thing, right? And if I was to integrate that flux form over the sphere of radius r, you can calculate that what that works out to is 4 pi. Because it's a standard surface integral. You can work out the surface integral of that vector field over the unit, over the sphere of radius r. You get 4 pi independent of the radius. On the other hand, yet the differential of this is the divergence of that vector field times dx wedge dy wedge dz, and it just so happens that that is equal to 0. Context, though. So what's the context here? Where is the vector field not defined? Right. So we're talking about on R3 with the origin removed. So if we puncture a point out of the, remove a point from R3, then there exists this 2 form, all right, which is closed, right? But it is not exact. See, because if it was exact on R3, then of course you could write this as the integral of d some phi, right, over SR, which then you could you know, you could use the generalized Stokes theorem to say, oh, so it's the same as the integral of the boundary of the sphere of radius r of dd of phi, right? But the funny thing is that the boundary of the sphere is empty, so this is identically equal to 0. All right. Now it turns out that these examples are very telling. They're saying something about the topology, actually. They're telling us something about the topology of the punctured plane, or the punctured 3 space. They're saying that there's something non-trivial about their topology. For the punctured 3 space, there's some kind of defect in the space where if you had some sort of balloon, you can't deform it to a point. There's that origin which you can imagine like a balloon trying to shrink it to a point. You can't because of the origin. For this one, you can't deform a loop to a point because you get stuck on the origin. So
The topology is trivial. What?
Hmm?
When you say the topology is trivial, what do you mean?
Non-trivial.
Then one with the opposite be.
What would non-trivial? Well, trivial topology would just mean that the
Just the set itself.
just when I think of a trivial topology, I think of something just like Rn. Now the definition, the Rahm cohomology. So you define ZP of U, which is by definition phi in P forms over U, all right, such that phi is closed. In other words, it's the kernel, it's really the kernel of the differential, it's the kernel of the exterior derivative as it is applied to P forms, right? It's in fact the kernel of the exterior derivative. And on the other hand, you can talk about, so this is the space of closed P forms, right? You can also talk about B upper P of U, which is by definition P forms, such that they're exact. And convention, which I'll write here, although I don't think we're going to get into enough detail for it to matter. The B upper zero of U is by definition just the zero space. So the de Rahm cohomology groups are defined by the quotient of closed by exact. HP of U is equal to the quotient space of the closed forms by the exact forms. All right. And the dimension of HPU is equal to the pth Betti number. That might look familiar. You know. Let's see here. So what does example 1 and example 2 tell us in terms of this language?
It can be closed.
Yeah, so example 1 says that there exists a closed form on the punctured plane, right?
Yeah.
Which is not exact.
But all the exact ones are closed.
Right. So two differential forms would be like cohomologous if they differ by the exterior derivative of a potential function. Anyway, basically what example 1 does is it indicates that, hey, there's a non-trivial topology in terms of there exists a closed form which is not exact, which means that this quotient is non-trivial.
And
Like,
that's a subset. B of U. A subset of C.
it better be if we're quotienting by it, yeah.
What I'm saying is that all the fees that are exact are also closed. Right?
Yes.
Yeah. I see. Okay.
It's a quotient vector. It's a quotient vector space. So like the thing is that the omega, like the equivalence class that you build from omega in my example 1 gives you a non-trivial cycle for this quotient. And likewise, if you look at 2 forms, example 2, that's an example of a non-trivial a cycle, a closed form which is not exact. So that speaks to the non-triviality of H2. Now, more calculation would be required to actually calculate the homology groups, I suppose. But I think it can be proved that the, I mean, well, we calculated, I think we calculated this already, right? Because the punctured plane, right? So the plane with just one point removed, I think, well, I should be careful. I'm trying to remember what that's, homea words. Good grief, forgot my words. Homeomorphic, I believe, yeah. So a homeomorphism, well, you take topology, you know these things, right? Homeomorphism, continuous with continuous inverse, a bijection, right? So we worked out the Betti numbers for the circle and the disk. I think the disk is the relevant one here. Could be wrong. Well, I'm fuzzy, so let me not say anything more. But anyway, enough. You know, you'll hopefully in grad school you'll get to take a course on algebraic topology proper, and you'll learn this. But anyway, the larger point here is that cohomology, the Rahm cohomology, actually uses differential forms to understand the topology of space, as compared to what we're doing like the last couple classes with looking at the triangulations and the boundary operator. The reason it's a cohomology and not homology is has to do with the direction. So like if you were to draw, so we had chains in the other thing, right? And you remember you had like chain, I don't know, like the one chains, right? And you had like two chains and then one chains and so forth, right? Zero chains, oops. And you remember the boundary operator went this way, right? But if we're talking about two forms and three forms and four forms, you know, the differential goes like that, right? So the difference is that the differential goes up the index of the things, whereas this one goes down. So homology versus cohomology, something like that. There is much more to it than that, but that's part of it. All right, so what is the Poincaré Lemma? The Poincaré Lemma has to do with when there is a converse to this theorem. So sometimes there is a converse to the theorem. Sometimes it is in fact true that closed implies exact. All right. So when is it the case that closed implies exact? When is closed a sufficient condition to suggest the existence of a potential function, a potential form rather, for a given closed form, right? So the Poincaré Lemma gives an answer. And it's not really, well, all right, let's see here. I've lost it. Where did I lose it to? Whoa. All right, let's get to it here. I gotta be careful, otherwise we're gonna run out of time before you know it. This actually does have some kind of interesting calculations, so all right, come on, where'd you go to? Well, I've got the proof before usually I put well, great. When am I going to actually say it? Oh, finally. Here it is. It's my proposition 10.6 on page 226, but about the 3 pages before that build up to it, but here it is. And so the words in this theorem make sure I don't have a better statement of it later. Nope. Here it is. if U, a subset of R, oh man, seriously? Rn, good grief, that's an Rn, is deformable to a point P, that's a big P, all right, big P, then a little p form gamma on U is closed if and only if gamma is exact. And that is the Poincaré Lemma, or at least one statement of it. So you may recall this from Calculus 3. The version of this that you see in Calculus 3 is that if the curl of a vector field, is 0 on a simply connected region, then that implies the vector field's a conservative vector field, which is to say that it's equal to the gradient of a potential function, which is to say that the corresponding work form for the vector field is exact. So that's an application of this. That's a special case, three-dimensional case. The two-dimensional case of this is that closed condition you saw in didn't see in differential equations. In differential equations, you study something called exact equations. An exact equation is like this: m dx plus n dy. It's equal to the differential of a function if and only if it's an exact differential equation. So one of the theorems you learn there is that if partial m partial y is equal to partial n partial x on simply connected domain, then there exists an f such that, m dx plus n dy is equal to the total differential of f. And in that case, the solutions to the differential equation, I really shouldn't write the f here, maybe 0 here. That's an exact differential equation if and only if there exists a level function whose the total differential of the level function is in fact the differential equation which you're given, in which case the solutions to said differential equation are just the level curves. They're just the level curves of big F, all right? Now, the condition which we teach in differential equations is that one way you can check for that is if these mixed partials are 0. If they are, then if that's true on a simply connected set, there exists a solution in the level curve. But that is nothing more than taking the exterior derivative of this see that? This is nothing more than partial m partial y dy wedge dx plus partial n partial x dx wedge dy, right? So this is d omega, if you like, which is of course partial n partial x minus partial m partial y dx wedge dy. See, if you're defining the differential equation by its so-called Pfaffian form, which is to say m dx plus n dy, a differential equation can be defined by a one form. So if we define the differential equation by the one form, it's an exact differential equation if and only if the differential of that one form is in fact 0. That is to say that omega is closed. So if it's closed on a simply connected space, then it's exact. But the cool thing here is if it's exact, that actually tells you how to solve the differential equation. The solution, you know, the solution then is precisely level curves of f. Here's a stupid example. If I have the differential equation 2x dx plus 2y dy equals to 0, well, that's the differential of x squared plus y squared equals to 0. The solutions to that are x squared plus y squared equals to r squared. Hooray! because it's easy to see that the exterior derivative of that differential equation is exactly 0, which is to say that the one form defining the differential equations is closed, hence exact, since it's true on R2. And of course the solution set is of course circles concentric about the origin. One of my favorite differential equations. Yeah, so I just pausing before I get into the general proof to show you that this is many things that you've already seen in math as you study exact equations, the conservative vector field theorem in Calc 3, but this is an n-dimensional thing. All right, so how do you prove that? Okay, good, we're only at 12. Like, whew. All right, so it's going to take me a few minutes to prove this. And along the way, we're going to define what deformable means. All right. So we have to go back and we have to build this up. And so, all right, like I said, be patient. We have to build some toys before we play. So the first thing is I have to let's see here. So what I'm going to do is I'm going to look at some kind of stack, if you will. I don't know why I made this so complicated looking. It's dumb. It could have just been a stack of pancakes. It doesn't really matter. The point is that there's a set. It's deforming. Try that again. I don't know. So this is my set U, all right, and I am so like the top thing here is up here we have one Cartesian product with U, and at the base, I've got this one down here is 0 Cartesian product with U. And so like maybe in the middle, we're looking at like t equals to 1/2. So here's t equals to 1, t equals to 0 here. All right. And so I'm like, okay, so we go J1 takes me up here, J0 takes me down here, and let's see here, what else can I tell you? We're assuming this mapping J, like J1 of x is equal to 1 comma x, and J0 of x is equal to 0 comma x. Yes. So let's see here. Let me be more specific here. So J1 is a mapping from U to I cross U. And J2 is also a mapping from U to I cross U. For what it's worth, not J2, there's no J2, that was J0.
What is I?
And I here is the 0 to 1 closed interval. Now this is all taken from, there's a book by Flanders. It's a Dover book on differential forms, which is one of the only ones I could afford for a while. You know, if I'd asked my parents to buy me books on differential forms, they would have bought them for me. I just never, never occurred to me, hey, maybe I should ask my parents if they buy me some books. Duh. I mean, they paid for my tuition. They would have bought me some books. Duh. We have not because we ask not sometimes, you know. But anyway, I used to rely more on Dover books than I do now. And so like Flanders differential forms book was a great resource because it's this little Dover book on differential forms that was born out of a seminar between engineering and math at Purdue in the 60s. And this book by Flanders, it has some really tough calculations on differential forms. It was always an intriguing book to me because it was almost impenetrable as an undergraduate to try to understand bits of it. But it does actually have a pretty good proof of the Poincaré Lemma, which I'm going over right now. So Flanders, it says, encourages us to view I cross U as like a cylinder where the J1 maps us to the top of the cylinder and J0 maps us to the bottom of the cylinder, like that. It said we can pull back forms on the cylinder to U on the top or from the base, right? In other words, if we could, let's see here. So, like over here, essentially the coordinate system is Tx, right? Whereas the coordinates over here are just x, and this is a subset of Rn, right? So here we're in n+1 dimensions, where we're just replicating the set U over and over again as we range t 0 to 1. But like a generic, let's see here. We could, for example, we could consider omega equal to x plus t dx plus dt. That would be a, I suppose that would be a 1 form, right, for n equals 1 case. And n equals 1, that's all you got, right? You got 1 forms. That's your top form, yeah. But if we, on the cylinder, we've got, if U is 1-dimensional, then the cylinder is still 2-dimensional. Anyway, so what's the pullback under J0 of omega? What's the pullback under J1 of omega? This is really just to get us warmed up, all right? Although it's kind of relevant because remember, if we understand how the pullback works on 1 forms, the fact that the pullback commutes with wedges means that if we understand how it goes for 1 forms, we can understand how it goes for K forms because the pullback on the 1 form basis translates to the pullback on the whole thing. This is really it. So all that means, the pullback under J0, so like what does J0 do? It leaves x as x, right? And it puts t equals to 0. So we just basically plug t equal to 0 up in here and we get ourselves an x dx. Right? On the other hand, pullback under 1, we're going to get x plus 1 dx, right? And I don't think we get a dt at all because dt is 0. See, t is constant. So like dt is equal to 0 in any of these slices. Yeah. All right, so now that we got that, we define something called big K. Now, if I had to guess, I would wager this whole construction goes back to like Cartan or something. I don't know, like, I have a strong feeling that this is something that is known from the literature before Flanders. Like, I don't know. But anyway, define. I would be curious the origins of this calculation is all I'm trying to say. Define smooth mapping K of P plus 1 forms on the cylinder to P forms on U as follows. Number 1, K of a of t comma x dxi is equal to 0. Number 2, k of a of t comma x dt wedge dxi, dxj rather, I'll use a different letter, j, is equal to the integral from 0 to 1 of a of t comma x dt dxj. And this is for multi-indices I of length p plus 1 and multi-indices j of length p. The cases 1 and 2 simply define the possible monomial inputs from p plus 1 forms on the cylinder into forms that have dt in those which don't. All right, so then k is defined for a general p plus 1 form on the cylinder by linearly extending these rules. Okay? Does that make sense? I mean, you could say, okay, but why? I think that would be a fair why? All right, why would be a pretty decent question to ask here. All right, so then there is something that we can prove from that called the K-Lemma. Lemma. So the K-Lemma. It says this: if omega is differential form on the cylinder, then k of d omega plus d of k acting on omega is equal to the difference of the pullback under J1 of omega and the pullback under J0 of omega. That's a very neat formula. That's a very neat formula because it, well, let's kind of look ahead. Think about this, right? Like, it's like in the case that d omega was 0, it's telling you that k of omega maybe could be a potential form if these are equal. Anyway, you can start to see how this possibly could be helpful for the question of how to construct a potential form. I don't think it's clear yet, right? It's not clear yet. So how do you prove this? The answer is one step at a time. Okay, so, all right, so let's work through it. Case 1. Case 1 would be the case that omega has no dt in it, all right? So a differential form on the cylinder, it's either got a dt in it or it doesn't, right? So essentially we'll focus our attention on monomials forming a p form. So, all right, so case 1, if omega is a of t comma x dxi, and that's a multi-index, okay? Then k of omega is equal to 0 by construction, right? Therefore, the exterior derivative of k omega is equal to 0, all right? But d omega is what? It's dA wedge dxi, which is going to give us partial a partial t dt wedge dxi, right? Because well, I guess I don't say that. Huh. I was thinking that had to be 0 I was thinking that had to be 0 because it was going to have too many dx's in it, but I'm assuming that I is a top index on u. That's not assumed here. It's a p form. So you can go to p plus 1. So I can't, I'm assuming too much here. So there's also the sum over j, right, of like partial a, partial x, j, dxj, wedge dxi. Okay, there's also that. I was thinking that wouldn't be there because this is automatically 0, but we're not assuming that the form is at the top. You know, this could be a 5-dimensional, u could be 5-dimensional, this could be a 3 form. You know, fine. All right, so then what? So now we can calculate, now we can try to calculate the, you know, so we know that the d of k omega is 0. And now we're trying to calculate the k of d omega. So what's k of d omega? Right? But we defined it by a linear extension, so, right? So you tell me what the second thing is here. No dt. By definition, this is 0, right? That's case 1. On the other hand, this one, we're supposed to do. Okay, good. I was worried that it was. So this we're supposed to do integral from 0 to t of partial a, partial t, you know, at t comma x, dt, and you got your dxi out there, right? Fundamental theorem of calculus. This gets you a of, this is supposed to be 0 to 1, right? I'm a dummy. So a of 1x dxi minus a of 0x dxi, right? But what is that? What are you doing? Like compare this and the initial form omega, or this. We're just doing what? We're putting t equals to 0, t equal to 1, or we're putting t equals to 0. That's precisely the pullback of the form omega under the J1 or the J0 map. Right? That is precisely, yeah, J1 pullback omega minus J0 pullback omega. Right? And we proved it. See, because you can, you know, d of k omega is 0, right? So now that's just case 1, right? What's the other case? Case 2 is what? What if our differential form has a dt, right? So we can have omega equal to a of t comma x dt wedge dxj, right? Then d omega is a little bit more complicated. It is the sum over j. Well, it's a little bit less complicated in another sense, because now the time derivative and the exterior derivative is automatically irrelevant because dt wedge dt is 0. So we just have partial a, partial xj, dxj, wedge dt, wedge dxj, right? Big J. And as such, right. So I guess I'm trying to think if I do anything more with that than that. Fine. So we can rewrite that as minus the sum partial a partial xj dt wedge dxj wedge dx big J, right? I just flip-flop for the minus. Great. Okay, so now basically to prove the K-Lemma, we need to, I think this one meets in the middle. I think this one we have to meet in the middle, like the proof-wise, if I remember right. It's been a little bit since I proved this, but yeah. So if we take K of d omega, how's that go? So it's got a dt in it, right? So we have minus the sum over J of the integral from 0 to 1 of partial a partial xj dt, right? dxj wedge dx big J, which of course gives us minus the sum over J of like partial a partial xj at 1 comma 0 dxj. Well, let me just, if you don't mind, I'm just going to pull that out. So minus, I'm just going to write it once, but understand we can multiply it through, right? That was not a 0, that's an x, right? So on the one hand, we have that. All right. Oh, wait a minute. I said we cannot oh, I'm a dummy. We can't do that. We can't do that. That's just nonsense. Why can't I do that? I'm such a dummy. Is this a t derivative? No. So can I do fundamental theorem of calculus? No. Dummy. It's just that. For now. On the other hand, we can calculate the differential of k of omega. I'm going to try to do that. So that is going to be the differential of the integral from 0 to 1 of a of t comma x dt, right? Wedged with dx upper big J. And so that is explicitly partial t of the integral from 0 to 1 of a of t comma x dt dt. Maybe I should put a t bar here or something to emphasize that that's a dummy variable of integration, right? Wedged with dxj plus the sum over J of partial xj of the integral from 0 to 1 a of t comma x dt dxj wedge biostatistics, who cares? There you go up, there you go. It's your new home. dx big J, right? All right. But the thing is, this is constant in t because, again, it's the t dependent. There's no t dependent. It's a definite integral. It's a number that differentiates to 0. And then we've got this piece over here, right? Which I can pull the derivative inside. Ooh, look at that. Here we go, that step. Integral from 0 to 1 of partial A partial xj t comma x dt dxj wedge dxj So what does that say? Apparently, d of k omega plus k of d omega, in this case, so you got your minus Pac-Man up here, you got your Pac-Man down here, so you got Pac-Man minus Pac-Man equal to 0. So what about these guys in this context? But you see that they both pull back to 0 because they've got the dt, right? So the dt pulls back to 0 under J0 and J1. So because of that, these are both identically 0. And woohoo! All right. So there's the K-Lemma. Okay? Sorry, that was going to happen. My apologies. At least I didn't make my joke about K-faces in the last lecture. All right, so I just kicked the camera. Let me double check on my... Yeah, we're okay. Okay, so I think I can erase this picture. No, I will not erase the picture. Oh, well, I can erase this proof. I can erase this proof. All right. That's what I should do. All right. Okay, great. So, at last, we will define deformable to a point. Okay. This is kind of fun. The end of advanced calculus ends up doing a little bit of algebraic topology in topology because it's just part of mathematical physics. It's just you can't avoid it. So here we go. Definition. U, a subset of Rn, is deformable to P, I'll do big P, if there exists smooth mapping G from the cylinder I cross U to U, such that G of 1 comma x is equal to x, and G of 0 comma x is equal to P for all x in U. So let's see, in terms of the language of the J0 and the J1, we have this, right? G of J1 of x is equal to x, and G of J0 of x is equal to P. In other words, if the space is deformable to a point, we have that G composed with J1 is the identity on U, and we have that G composed with the J0 map is the constant map P. Ah,